Thank you for watching our presentation. I'm Masami Endo, a PhD student at Keio University. In this video, we present a risk-aware path planning method for planetary rovers exploring heterogeneous deformable terrains. Safe rover navigation requires traversability evaluation in planetary exploration missions by detecting geometric obstacles such as natural rocks and predicting wheel slip on deformable surfaces, which can eventually cause permanent entrapment. However, wheel slip is difficult to assess due to its complex physical phenomena and becomes more complicated when traversing heterogeneous terrains. Machine learning is useful for predicting such traversability, but erroneous predictions endanger rovers. Machine learning models often predict traversability from visual information. For heterogeneous terrain, classification models are used to identify distinct terrain types. Regression models, such as Gaussian processes, further predict slip as a probability distribution for identified terrain classes at arbitrary positions. However, machine learning models inevitably carry the risk of erroneous traversability predictions, such as due to wrong terrain classification or slip prediction, and eventually lead to rover immobilization. To address this issue for safe rover navigation, we propose a new path planning algorithm that explicitly considers the potential for erroneous predictions. For a given problem instance, the optimal path planning problem is formulated to find a path from the start to the goal with a minimal cost due to wheel slip. We employ a terrain classifier to pixel-wisely predict terrain classes from appearance imagery and Gaussian processes to model class-dependent latent slip functions with geometry information. Our key idea is the probabilistic fusion of terrain classification and slip regression models. This allows a multimodal slip prediction on heterogeneous terrains while expressing overall uncertainties from machine learning models. Given the distribution, we define slip as risk to comprehensively evaluate risk due to slip, such as rover immobility and disk control, by assuming the flat ground traversing is least risky. The fifth distribution further enables conservative risk assessment via condition value at risk, accounting for less likely occurring slips in the upper tail to derive risk-aware travel time costs for path planning. Simulation studies with varying difficulties in traversability prediction investigate the proposed path planning method. We prepare three synthetic datasets for path planning problems named standard, erroneous slip, and ambiguous appearance to validate the robustness of our method against unreliable traversability prediction. The standard dataset adopts a simple setting where pixel color identifies terrain classes and slip measurements contain slight noise. The erroneous slip dataset has a more complex setting with greater noise in slip measurements, which can occur due to factors like insufficient in-situ measurements and unobservable terrain conditions. We replicate another setting in the ambiguous appearance dataset with multiple terrain classes having the same appearance, assuming situations such as visually similar terrain classes or one material covering another. The proposed planner successfully navigates the rover on a less slippery path even when machine learning predictions are erroneous due to ambiguous terrain appearance and unreliable slip models. From the quantitative comparison, our proposed approach owns the highest performance in terms of safety to avoid immobilized situations due to slip during path execution. By leveraging the MJP, we can generate a slip distribution encompassing a wider range of slips than single Gaussian processes. Without MJP, rovers may struggle to traverse due to significant prediction errors from incorrect sleep models. VAR and CVAR are necessary for rational risk evaluation to see less likely occurring slips in the distribution, enabling successful rover traverse in challenging environments. Finally, a parameter study for the ambiguous appearance dataset is conducted to see the effects of the confidence level alpha against our CVAR-based approach. The results indicate alpha dominates the trade-off between safety and efficiency. From the results, simple parameter tuning can control planning behavior depending on the required mission timeline. Thank you for your attention. I'm glad to hear any questions.